Hello and welcome. Today we're embarking on a fundamental topic in linear algebra, eigenvalues and eigenvectors. By the end of this lesson, you will be able to define eigenvalues and eigenvectors, understand their geometric significance, and learn how to calculate them for a given matrix. These concepts are not just abstract mathematical ideas. They are powerful tools used in countless fields, from physics and engineering to computer graphics and data science. So what exactly are they? Let's start with the core definition. An eigenvector of a square matrix A is a non-zero vector, versus that, when multiplied by A, results in a scalar multiple of itself. The scalar, lambda, is called the eigenvalue. This relationship is captured by the equation A times versus equals lambda times versus here A is our matrix, V is the eigenvector, and lambda is the eigenvalue. Let's break down what this means geometrically. Imagine a vector V in space. When you apply a linear transformation represented by matrix A, the vector V is transformed into a new vector, AV. For most vectors, this transformation will change both the direction and the magnitude of the vector. But for an eigenvector, something special happens. An eigenvector is a vector that, after the transformation, remains on the same line through the origin. It might be stretched or shrunk, or even flipped, but its direction doesn't change. The eigenvalue lambda tells us the factor by which it's scaled. So eigenvectors are the special vectors that are only scaled by the transformation, and eigenvalues are the scaling factors. This property makes them incredibly useful for analyzing the behavior of linear transformations. Now that we understand what eigenvalues and eigenvectors are, let's learn how to find them. This is a two-step process. First, we'll find the eigenvalues using the characteristic equation. Second, we'll find the corresponding eigenvectors for each eigenvalue. Let's start with the first step. We begin with our defining equation, A times versus equals lambda times versus. To solve for lambda, we need to rearrange this equation. A common mistake is to divide by V, but we can't do that since V is a vector. Instead, we'll use the identity matrix I. We can rewrite lambda times V as lambda times the identity matrix I times versus. This is because multiplying by the identity matrix doesn't change the vector. Now we can move the term to the left side, giving us A times versus minus lambda times I times versus equals the zero vector. We can factor out the vector V, which gives us the matrix A minus lambda I times versus equals the zero vector. This is a homogeneous system of linear equations. We are looking for a non-zero vector versus. For this system to have a non-trivial solution, a solution other than V equals 0, the matrix A minus lambda I must be singular or non-invertible. A matrix is singular if and only if its determinant is 0. This gives us our characteristic equation, the determinant of A minus lambda I equals 0. Solving this polynomial equation for lambda will give us the eigenvalues. Once we have the eigenvalues, we can substitute each one back into the equation, A minus lambda I vi equals 0, and solve for the corresponding eigenvectors versus. Let's see this in action with an example. Let's work through our first example. We'll find the eigenvalues and eigenvectors for a 2 by 2 matrix. Consider the matrix A equals 2, 1, 1, 2. Step 1. Find the eigenvalues using the characteristic equation. We need to solve the determinant of A minus lambda I equals 0. First, let's construct the matrix A minus lambda I. We subtract lambda from the diagonal elements of A. This gives us the matrix 2 minus lambda, 1, 1, 2 minus lambda. Now, we calculate the determinant of this matrix. For a 2 by 2 matrix, the determinant is the product of the diagonal elements minus the product of the off-diagonal elements. This gives us 2 minus lambda times 2 minus lambda minus 1 times 1. Expanding this, we get 4 minus 4 lambda plus lambda squared minus 1, which simplifies to the quadratic equation lambda squared minus 4 lambda plus 3 equals 0. We can factor this equation into lambda minus 1 times lambda minus 3 equals 0. This gives us our two eigenvalues, lambda equals 1 and lambda equals 3. Now that we have our eigenvalues, lambda equals 1 and lambda equals 3, we can proceed to step 2, finding the corresponding eigenvectors. We'll do this by solving the system a minus lambda I v equals 0 for each eigenvalue. Let's start with our first eigenvalue. Case 1. Lambda equals 1. We substitute lambda equals 1 into our matrix A minus lambda I. This gives us 1, 1, 1, 1. We need to solve 1, 1, 1 times versus equals the 0 vector. This matrix corresponds to the system of equations v1 plus v2 equals 0 and v1 plus v2 equals 0. These are the same equation. This is expected as the matrix is singular. From this we can see that v1 equals negative v2. We can choose any non-zero value for v2. Let's choose v2 equals 1. Then v1 equals negative 1. This gives us the eigenvector v1 equals minus 1, 1. Now for the second eigenvalue. Case 2, lambda equals 3. We substitute lambda equals 3 into our matrix A minus lambda I. This gives us minus 1, 1, 1, minus 1. We solve minus 1, 1, 1, minus 1 times versus equals the 0 vector. This corresponds to the system negative v1 plus v2 equals 0 and v1 minus v2 equals 0. Again, these are equivalent. From this, we see that v1 equals v2. Let's choose v2 equals 1. Then, v1 equals 1. This gives us the eigenvector v2 equals 1, 1. So for the matrix A, we found two eigenvalues, 1 and 3, with corresponding eigenvectors minus 1, 1, and 1, 1. Let's quickly verify one of them. Let's check the second pair. A times v2 is 2, 1, 1, 2 times 1, 1, which equals 3, 3. And lambda times v2 is 3 times 1, 1, which also equals 3, 3. It works! We have successfully found the eigenvalues and eigenvectors. Let's try a second example, this time with a 3 by 3 matrix. The process is the same, but the algebra will be a bit more involved. Consider the matrix B equals 1, 0, 0, 0, 2, 0, 0, 0, 3. Step 1. Find the eigenvalues. We set the determinant of B minus lambda I to 0. The matrix B minus lambda I is 1 minus lambda, 0, 0, 0, 2 minus lambda, 0, 0, 0, 3 minus lambda. This is a diagonal matrix. The determinant of a diagonal matrix is simply the product of its diagonal entries. So we have 1 minus lambda times 2 minus lambda times 3 minus lambda equals 0. This equation is already factored, so we can immediately see the eigenvalues are lambda equals 1, lambda equals 2, and lambda equals 3. This example highlights an important property. For a diagonal matrix, the eigenvalues are simply the entries on the main diagonal. This is a very useful shortcut. Now for step 2, finding the eigenvectors for our diagonal matrix B. We'll solve B minus lambda I, v equals 0, for each of our three eigenvalues. Case 1, lambda equals 1. Substituting lambda equals 1, we get the matrix 0, 0, 0, 0, 1, 0, 0, 2. We solve this times versus equals 0. This gives us the system v2 equals 0, and 2 times v3 equals 0. This means v2 and v3 must be 0, but v1 can be anything. We choose v1 equals 1. So the eigenvector is v1 equals 1, 0, 0. Case 2, lambda equals 2. Substituting lambda equals 2, we get the matrix minus 1, 0, 0, 0, 0, 0, 0, 1. This gives us the system negative v1 equals 0 and v3 equals 0. So v1 and v3 are 0 and v2 is free. We choose v2 equals 1. The eigenvector is v2 equals 0, 1, 0. Case 3. Lambda equals 3. Substituting lambda equals 3, we get the matrix minus 2, 0, 0, 0, minus 1, 0, 0, 0. This gives us negative 2 v1 equals 0 and negative v2 equals 0. So v1 and v2 are 0 and v3 is free. We choose v3 equals 1. The eigenvector is v3 equals 0, 0, 1. Notice a pattern here. For a diagonal matrix, the eigenvectors are the standard basis vectors. This is another useful property to remember. Let's do one more example, this time with a repeated eigenvalue. Consider the matrix C equals 2, 1, 0, 2. Step 1. Find the eigenvalues. We set the determinant of z minus lambda I to 0. The matrix C minus lambda I is 2 minus lambda, 1, 0, 2 minus lambda. This is an upper triangular matrix. The determinant of a triangular matrix is also the product of its diagonal entries. So we have 2 minus lambda times 2 minus lambda equals 0. This gives us a single eigenvalue, lambda equals 2, with a multiplicity of 2. This means the root 2 appears twice in the characteristic equation. This is another important property. For any triangular matrix, upper or lower, the eigenvalues are the entries on the main diagonal. Now for step 2. Finding the eigenvectors for our repeated eigenvalue. We only have one eigenvalue, lambda equals 2, so we'll solve C minus 2, IV equals 0. Substituting lambda equals 2, we get the matrix 0, 1, 0, 0. We solve this times versus equals 0. This corresponds to the system. V2 equals 0 and 0 equals 0. This means V2 must be 0, but V1 can be anything. We choose V1 equals 1. The eigenvector is V equals 1, 0. Notice something interesting here. The eigenvalue lambda equals 2 has a multiplicity of 2, but we only found one linearly independent eigenvector. This is a key concept. The algebraic multiplicity of an eigenvalue is the number of times it appears as a root of the characteristic equation. The geometric multiplicity is the number of linearly independent eigenvectors associated with that eigenvalue. For our matrix C, the algebraic multiplicity of lambda equals 2 is 2, but the geometric multiplicity is 1. In general, the geometric multiplicity is always less than or equal to the algebraic multiplicity. When they are not equal, the matrix is called defective. Let's recap what we've learned so far. We've defined eigenvalues and eigenvectors, and we've seen the step-by-step process to find them. First, we find the eigenvalues by solving the characteristic equation, the determinant of A minus lambda I equals 0. Second, for each eigenvalue, we find the corresponding eigenvectors by solving the homogeneous system, A minus lambda I, V equals 0. We also saw some important properties. For diagonal or triangular matrices, the eigenvalues are simply the diagonal entries. We also introduced the concepts of algebraic and geometric multiplicity, noting that the geometric multiplicity is always less than or equal to the algebraic multiplicity. Now, let's test your understanding with a practice problem. Find the eigenvalues and eigenvectors of the matrix D equals 3, 2, 3, minus 2. Pause the video and give it a try. Welcome back. Let's go through the solution. First, we find the characteristic equation. The determinant of d minus lambda I equals 0. This gives us lambda squared minus lambda minus 12 equals 0, which factors into lambda minus 4 times lambda plus 3 equals 0. So, our eigenvalues are lambda equals 4 and lambda equals minus 3. For lambda equals 4, we solve d minus 4, I via v equals 0, which gives us the eigenvector v1 equals to 1. For lambda equals minus 3, we solve d plus 3i, v equals 0, which gives us the eigenvector v2 equals 1 minus 3. Great job if you got that right. In our next video, we'll explore more properties of eigenvalues and eigenvectors, and we'll see how they lead to the powerful concept of matrix diagonalization. Thank you for watching.